Annenberg Media.
Everybody has heard that there's an energy crisis. People are always telling us that we must help conserve energy. Well, I've got news for you. It's impossible. I don't mean it's impossible to conserve energy. I mean it's impossible not to. Energy is always conserved no matter what you do. That's one of the most fundamental laws of physics. In fact, we'll soon find out that there are 3 conservation laws. The conservation of energy, momentum, and angular momentum. These 3 great conservation laws are the crown jewels of physics. 3 quantities that are never created or destroyed. The amount of them is the same now as it's always been and always will be forever. And so what is this crisis we keep hearing about? Could it be a breakdown in the very laws of physics? Just try to imagine this scene. The President of the United States, in the Oval Office, all 4 national networks are there broadcasting. He looks straight into the television screen, radiating sincerity, and he says, "My fellow citizens, in this hour of crisis, we must all work together to help conserve angular momentum." Now, wait a minute. Obviously, there's something wrong. Something is special about energy. But to understand what, we must first understand what energy is.
Energy, in every shape and form, around the Earth and throughout the universe. Energy is provided by nature. Even if some of it, in a deadly game of follow the leader, is unleashed by man. Energy, and more energy. No matter how, or how often it's used, regular or unleaded, energy is always conserved. But if that's a fact, and the law of the conservation of energy says it is, why isn't there always enough energy at hand? Motion itself is a form of energy, because energy takes that form when anything moves. But if energy is always conserved, how do moving objects ever get started? And once running, whatever direction they're moving in, if energy is always conserved, how can they ever stop? Some people work with more and more weight. Others try to work off some of the weight they walked in with. Yet even here, the vital question is, if energy is always conserved, why do muscles get tired? And why do weights fall? The answer, like exercise in general, has to do with work. In fact, part of the answer is work. And in exercising the conservation of energy, work has a precise definition. The greater the weight, the more strength required to lift it, of course. And the greater the height, the more work. Work equals force times height. When the work is being done near the surface of the Earth, the force in this equation is the constant force of gravity, which equals mass times the acceleration of gravity. So, work equals mass times g times height. Sometimes, force makes mass accelerate. But here, force is used to overcome gravity, to lift the weight to a certain height. In the conservation of energy, the role of work is to transfer energy from one place to another. From muscle into steel, for example. The barbell has energy because of its height. That's potential energy, which is given the symbol U. In a constant gravity field, the potential energy of any object is written as mgh. In other words, its potential energy is exactly equal to the work that was put into it. It's called potential energy because, at any given height, it's ready to go into action. The greater the height, the more potential energy stored in the weight. Potential energy that can change into motion. For all its ups and downs, potential energy depends only on vertical distance. But there must be an easier way to make the point. These machines, the mechanical ones, combine pulleys, cams, levers, and inclined planes that Galileo might have admired. A lot of expensive technology is at play here to increase or decrease, or just change the direction of the force needed to lift a weight. But no matter in what direction the force is applied, potential energy relates only to height. And the potential energy keeps changing. Every time anything moves up or down, potential energy by itself isn't conserved. In the law of the conservation of energy, then, what is actually conserved? Toward the end of the 16th century, Galileo Galilei asked himself a similar question. But it was one question for which even Galileo failed to find an answer. Nonetheless, while using inclined planes to slow down the acceleration of falling bodies, he did find something rather fascinating. No matter what path it followed, the ball would return to its original height, almost as if the ball remembered its original position. Of course, Galileo knew that an inanimate object couldn't remember where it had been. But he realized the ball retained something very powerful. If not memory, he wondered, what did the ball conserve? The answer didn't come speedily, but speed is the key to the answer. Starting from the same height, no matter what the slope of the incline, when the ball gets to the bottom, it's always going at the same speed. The energy of the ball's original height is still rolling along, transformed into speed. Human movement beautifully demonstrates how energy can change forms. Pushing a swing may not seem like work, but it is, and it increases the swinging girl's speed at the bottom of the arc and her potential energy at the top. So, while the flow of energy from one form to another may be child's play, it all begins with a little work. A little work is force through a little distance. But it all adds up, or in the language of calculus, it integrates.
If work is done against a constant opposing force, as in lifting a block from one height to another, the work is the difference between the potential energy at the two heights. That is, the change in potential energy. If work is done with no opposing force, the work is still force integrated over distance. But now the result of the work is to accelerate the block. In other words, it gains speed. So, what happens if we consider the interval in terms of speed? In terms of speed, the work is the change in the quantity 1/2 mv squared. This is a new kind of energy, an energy of motion. It's called kinetic energy.
It takes more than the speedy work of calculus to create the kinetic energy of a body in motion. These athletes work their bodies up to maximum speed and then use that kinetic energy to launch themselves across amazing distances. Of course, when they do that, they lose the kinetic energy they've worked so hard to build up. But if there are only two forms of energy, potential and kinetic, and neither is conserved, how can any form of energy be conserved? There's a simple yet powerful explanation, but it takes a little leap of imagination. Potential energy changes constantly, and kinetic energy is in a constant state of flux. But when the sum of kinetic and potential energy is considered together, the totality of energy is a constant. In other words, energy, E, equals potential, U, plus kinetic, K, and that's a constant. Potential energy of height changes into kinetic energy of motion. And back again. The ball doesn't remember its height. It conserves its energy until, when its energy is again all potential, it must be at its original height. Turning speed into height can be both a spectacular feat of coordination and an impressive demonstration of the relationship between kinetic and potential energy. In this case, the faster the run, the higher the vault. Muscles increase kinetic energy more and more, eventually to the limit of the athlete's ability. The pull changes all that kinetic energy into great potential. Suddenly, falling faster and faster, his accumulated potential energy changes back into kinetic energy. But something's wrong here. Now he has neither potential nor kinetic energy. And if energy is conserved, where did it go? Indeed, what happens to all the used up energy on Earth? In the end, kinetic energy and potential energy alike hit the dust. Nothing on Earth moves forever. The conservation of energy, the law of inertia, Galileo's law of falling bodies, these are notions of science, not science fiction. But to visualize them clearly, it helps to travel beyond everyday experience to a world almost without friction, where astronauts find that things work the way Galileo said they should.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct.
It took 400 years and billions of dollars. But even here, on the moon, a certain amount of friction still exists. But with or without friction, these cosmic explorers aren't the only ones who can slip up.
Oh, dadgummit.
Jack Schmidt, having a few problems.
Consider the controversial discovery of America. She might have been chanced upon by South Sea drifters. But speculative theories aside, historians generally agree that around 900 AD, the Vikings found these fields ripe for discovery, or rediscovery, as the case must have been. But that's another story. And in any case, America was the name that Europeans finally settled on. America was named after Amerigo Vespucci, an Italian who navigated first for Spain, then for Portugal. Though Amerigo really got around, he wasn't the first to set foot on the shores of the Americas. Neither was England's legendary explorer, Captain James Cook. And contrary to popular opinion, neither was Christopher Columbus. Nonetheless, Columbus usually gets credit for discovering the Americas. Not for when, but for how he got the job done. Columbus discovered America so well, so very well, that nobody had to come along and do it again. Not unlike any new world, the continent of physics was, and still is, ripe for discovery. The frontiers are rigorous.
Mannaggia, ma che è successo? Oh, scusatemi.
The discoveries sometimes shocking, and often very controversial. But throughout the land of physics, the rewards can be greater than the hardships. James Prescott Joule gets credit for discovering the law of the conservation of energy. He wasn't the first to explore the region, but like Columbus, he returned with maps that, from then onward, the rest of the world could follow with confidence. The son of a British brewer, Joule studied the efficiency of steam and electric engines for the family business. He devised an ingenious method of measuring how much mechanical energy turns into heat. A large weight, lifted to a certain height, has a precise potential energy, mgh. Joule arranged to have falling weights turn paddle wheels inside a carefully insulated container of water. Then, he measured the water's temperature. In this way, Joule showed that a given loss of potential energy always turns into precisely the same amount of heat. Joule's concept, this idea of loss and gain in relation to the conservation of energy, is virtually unknown here. And for the sake of this group's morale, ignorance is bliss. Consider the diabolical fact that kilocalories, commonly known to dieters as food calories, have a tendency to generate fat. For example, to burn off the 800 food calories from a single slice of chocolate cake, it would take this fellow about 2,000 lifts. And when you consider that the purpose of all this lifting, pushing, dancing, and bending is to get rid of potential or kinetic energy, the fact that all energy in every form is always conserved would be very depressing news for these people. Conserve it? Not at all. They want to waste it, lose it, use it up, and work up a good sweat. This machine, for example, is designed to waste energy. In fact, it could be seen as an extraordinary heater. The kinetic energy of any falling object is transformed into another kind of kinetic energy. The vibrations of atoms have a number of effects. They jostle the nearby molecules of air, which creates sound waves. And they always generate heat. The heat spreads from molecule to molecule, dissipating the energy, but never destroying it. Not even one erg of it. Energy that seems to vanish into heat is merely spreading into random vibrations, increasing the kinetic and potential energies of atoms by exactly the amount that's been lost. Throughout the scientific world, this activity can be measured precisely. Work, potential energy, and kinetic energy, each a form of the same basic quantity, are all expressed in the same unit, which is equal to 1 Newton meter. That unit, the joule, is slightly less than the energy of 1 pound lifted 1 foot. 4.2 joules are equal to 1 calorie, the standard measure of heat. Starting in nuclear fires within the sun, energy flows throughout the solar system, ever changing in kind, but always in the same amount. It reaches the Earth as light rays that energize the planet and everything on it. Only 2 forms of energy are mechanical: potential and kinetic. Work, force times distance, transforms energy, such as energy hidden in the biosphere, into the visible potential energy of the weight, poised high above the floor. Energy changes constantly, from potential to kinetic, from kinetic to potential, and back again and again, in countless ways. In whatever form, however, mechanical energy eventually begins to vanish once again, begins to disappear from sight and sound, not lost or destroyed, but transformed back into heat. Energy is never lost and always conserved, but dissipated into the random motions of countless atoms and molecules. Energy becomes harder and harder to retrieve, and almost impossible to make use of again. And whether or not these men and women are aware of it, That is, nonetheless, the inevitable end of all the energy on Earth.
So there you have it. Energy is conserved, but we render it useless. The energy stored in a liter of gasoline is released when it explodes in the pistons of your car. Some of that energy is temporarily turned into the kinetic energy of the motion of the car. But all of it, every bit of it, eventually winds up as useless heat at the temperature of the environment. And once that happens, it can never be returned into a liter of gasoline again. So you see, there really is a crisis. In a few decades, we're using up all of that fuel that it took the Earth millions of years to create. And once that's done, it can never be replaced. All of that stored energy has become useless. But even aside from the social problem, there's a philosophical point. We've learned today that there are certain things which, once done, can never be undone. Now, of course, everybody's always known that. But what we've learned today is that it's more than just a wise observation about the human condition. It's a basic law of physics. That new law has been expressed with great precision many times. But my favorite expression of it was made by an 11th century Persian mathematician named Omar Khayyam. He said, "The moving finger writes, and having writ, moves on. Nor all your piety nor wit can cancel half a line, nor all your tears wash out a word of it." Okay, I'll see you next time.
According to the law of the conservation of energy, although energy changes forms, the total amount of energy in the universe is always constant.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.